All right, guys. So, welcome back, everybody. Today, we're going to be discussing and talking about starburst, star formation. This will be the first part of the whole lesson on stellar evolution, which includes the birth and death of stars. Chapter 16 is about the birth, and chapter 17 will be about the evolution and death of stars. And in that chapter in particular, we're going to have to classify two particular paths. One, which is the low massive stars like the sun, one, which is the high massive stars, which in some way I already discussed that on what happens when a supergiant becomes a super red giant and how do they die, right? And the evolution path or the evolutionary path for a star like the sun. But in this chapter, we're going to be focusing on the star formation and star forming regions in the universe, in particular in our galaxy. Okay, so we're going to start with this picture here. What you see there is a nebula or a stellar cloud. The characteristics are basically the different colors. You see a very reddish color in most of the picture, and you see bluish in some parts of it. That already gives you the idea that there is something happening in there. The problem is that, as you know, the electromagnetic spectrum comes in different wavelengths, right? From radio to gamma wave. Visible light gives you a picture like that, but that's not enough information to know what's going on. Um, I will show you later also a picture of the pillars of creation, which are part of the Orion Nebula, and also from the Orion Nebula. And you will see that in visible spectrum, the nebula gives you very nice colors. For example, the red color, pink characteristic is emission from hydrogen alpha lines, emission lines of hydrogen. And the blue color is a characteristic of reflection nebulas, right? Light being scattered by stars. For example, the Pleiades, right? The Seven Sisters. But that's not enough to know what's going on. You need longer wavelengths to be able to penetrate within the cloud, right? For example, M17, which was the region I studied in my project for star forming regions. So stars forming nebulas. Now, why do they form? Because we need to, or to know why do they form, we need to understand the whole idea of gravity and heat, which is related to temperature. And also from those two concepts, you can understand the idea of contraction, pressure, and thermal radiation, right? Here's another picture that illustrates a whole bunch of, in fact, these are the Seven Sisters there. So the thing is that there might be a small emission nebula here surrounding it, and stars that are mostly blue and white, right? Some of them might be blue giants, some of them may be white giant stars like A stars, F stars, or B stars, sorry. And some of them may be stars like the sun, some yellow and reddish stars on the background. Why do we have regions that we cannot see? Some of them are called dark nebulas, all right, where light is not being able to scatter and doesn't reflect any light. Some of them is because of strong reddening. So what is reddening? Okay, before we go into that, let's understand the idea of a cloud. So a cloud is a very dark region of space, mostly made of dust and gas. And instead of just calling it space, we're going to call it the interstellar medium, which is the medium between stars. This is made of different structures. You have molecular clouds, which are the main source of star formation. There are dark nebulas, emission nebulas, reflection nebulas, and H2 regions and photodissociation regions. Now, in a physics course, you will study each one of those and the physics of cooling and heating. That is a very interesting subject, by the way. But the idea on this course is just to go into a stellar cloud, a star-forming cloud, all right? So let's think as a cloud as part of the interstellar medium, which is basically the gas between stars. The gas and dust, because space is also full of dust. So how do we study these clouds? As you probably know already, the best way to study clouds that they don't emit their own heat is by studying their emission lines. And by studying their emission lines, we see that they have a high, as we expect, a high abundance of hydrogen and helium. And then 2% of other elements, carbon, oxygen, nitrogen. Now, a cloud like that can heat up and then eventually shrinks. If there is enough heat, it will start nuclear fusion. Now, for that to happen, the cloud needs to collapse by its own gravity. So the mass of the cloud is important. So we need to think about temperature and gravity. Remember that temperature is a measurement of what? The average speed of the particles. And you also need to remember hydrostatic equilibrium, which is the equilibrium that is going on or happening in the stars between the pressure due to nuclear radiation, nuclear fusion, and gravity, the gravity due to its own mass. So temperature is related to the average motion of particles. But the thing about these clouds or molecular clouds in the interstellar medium, which, for example, this is a Horse Nebula in Orion, okay? They have very low temperatures. They can go from 10 to 30, maybe 100 kelvins, which is minus 200 or minus 173 Celsius. It's very, very cold. But even at that temperature, you can have some random motions of particles. All right? However, that wouldn't be enough. That wouldn't be enough, and the G-force will not be sufficient. So you need a lot of atoms for that cloud to collapse. All right? So there is a threshold density for these clouds to actually start producing stars. Now, most of the matter in these clouds is formed on these molecules. H2, which is your hydrogen recombined, so 2 atoms of hydrogen bond together, all right? And your carbon monoxide. But that's nowadays, though. Okay, so nowadays, after 13.8 billion years of expansion after the Big Bang, you can have molecular clouds that are made of this, right? These molecules, mostly hydrogen and carbon monoxide. And temperatures now, after the expansion, of 10 to 30 kelvins, and a density of 300 molecules per cubic centimeter, right? So that's cubic centimeter. If you want to do it per cubic meter, you will have to multiply that by 1,000,000. So that's a lot. All right. As you can see, the visible picture of the nebula just shows you the cloud. And then the radio image will start showing you emission of carbon monoxide here. All right. So most of what we know about molecular clouds, they come from observing the carbon monoxide. All right, that's the main molecule that composes this nebula. All right, so we look at those emission lines and we can find the temperature and the density of it. Okay, but when we look at these nebulas, regardless of where we are looking at, we always have this issue, the interstellar dust, which are very tiny particles, and they block our view and they produce reddening. What's the meaning of reddening? Is the fact that visible light cannot really penetrate, and the interstellar dust is not going to be able to glow past the visible light. So you have to use larger wavelengths to be actually able to observe through dust. And I know that very well because that was an issue I had in my project. When we had the data from the Spitzer, all the data was reddened, and we have to use interstellar extinction, which is a very simple equation, by the way. And you can correct the data for the extinction happening due to the dust. Look at the scale there. So those are very tiny particles, but they still can produce enough reddening to block our view of stars. They are mostly made of carbon, oxygen, silicon, and iron. Not surprisingly, because all of these elements are made in the core of stars, by the way. All right, all of these elements are made in the core of stars. So that makes sense. So this is an example of reddening. So that's how it can block your view, right? The cloud will look redder because that blocks visible light. So blue light is not being able to pass through as effective as red light. All right, so that's a visible image of a dark molecular cloud there. So yeah, you can tell there is something there, but you don't know what's inside. You don't know what's happening within the cloud. And we care about that. So when we start using infrared, look at the difference. This is a visible image. This is an infrared image. The infrared image already tells you that there is things happening. You see these glows? Some of it may be small fragments, and that's going to be key in star forming, by the way, star formation. But what you can see is stars or disks or protostars already forming in there. All right. So as it says there, observation of infrared light reveal stars on the other side of that cloud. All right. So dust, interstellar reddening, and infrared imaging are very important to study star formation. That is the introduction. That's what we need to know. All right. These are the pillars of creation, and you can tell why they call them like that, right? This was a picture from the Hubble, actually, when it was launched in the 90s, in 1993. Pretty nice. You can look at some of these stars glowing outside of the molecular cloud here, right? Which, by the way, if you are interested, some clouds can span to tens of parsecs. So you can have a molecular cloud which can be as big as the solar system. Okay, even bigger than that. So they are very vast. If I take a look at the infrared picture, now look what you can get. So it reveals newborn stars embedded inside it. Compare this to this, right? That's why it's very important to understand the electromagnetic spectrum. So now we know there is more information. And a radio image can also give you some of the emission lines and some of the contours in here. Remember that for the sun, we use X-ray imaging for the corona. So now you can see why we studied that before. So now you know how that's being utilized, right? So a cloud contains thousands of times the mass of the sun at a very low temperature. 10 to 30 kelvins, and they seem to have enough pressure to support them, right? Because they seem to just be there. However, they can ignite stars. But how will they ignite stars if they are just there, stable? Because they need to become unstable, all right? And there are different events for that to happen. Now, you can also have glowing dust grains. So when you look at emission nebulas like here, right, you can see that the dust absorbs visible light and they heat up, and that they emit light in the infrared wavelength. All right. So again, the dust can also be ignited or starts to glow because of all the thermal radiation, right? But as we know already, if you are in a cloud, the dust and the cloud itself will block visible light. So you can only observe the glowing dust grains in infrared in comparison with visible here. Look at the visible part there, right? And then compare it with like infrared there. Okay, that's why the James Webb Telescope is going to have infrared cameras, as you probably know, right? That's because it will be meaningless to just take pictures in the visible spectrum when a lot of information of the universe, like star formation, will come in the infrared wavelength, right? So when you want to study the beginning, especially for the beginning of a star forming, you want to use infrared light. Okay. Later on, when stars are being formed, when you have a Tauri stars, a protostar, and obviously a main sequence stars, you can already go into the visible light because there is no more dust and there's no more cloud surrounding it, right? And then you can actually see the star itself. Okay. So now we go into the main thing, right? So how does the cloud become unstable? Because you see a cloud, okay. I want to repeat what my supervisor told me in my project. You normally won't see clouds or H2 regions like that, right? I know that it will be very nice to see them like that. And we have seen some H2 regions in our galaxy that are very, very nicely shaped, but normally you don't see them like that. You normally see them like that or like in random shapes, right? And that's because normally when we spot them, they are already becoming unstable. And this can be triggered by another star or a supernova. If there is a supernova passing by the region where the molecular cloud is, it can create, make it unstable, and it can start igniting some star formation, right? In other cases, it can also be a shock wave, for example, from an O star or a B star. Remember that just like the sun, giant stars, they emit, right, radiation like solar winds. But obviously for a giant star or a supergiant star, those mass ejections, those solar flares will be much more energetic enough to trigger and to make a cloud like this unstable, right? Now, gravity versus pressure. So that is the key on this part. We need to understand that so far gravity and pressure are stabilized when the cloud is not being triggered and is stable. But once the cloud becomes unstable, then you have a battle between gravity and pressure. Remember that gravity can create stars only if they can overcome the thermal pressure in a cloud. So the cloud, even though it's cold, 10 kelvins, 30 kelvins, it has a lot of atoms. It has a large density, right? And you need to have enough gravity to overcome that thermal pressure inside the cloud, right? Emission lines, all right, can also prevent this pressure from building up, all right? So we are gonna have to deal with both things, gravity and emission lines pressure. And later on, I'm going to introduce a second form of pressure, because you can have pressure due to thermal radiation, thermal energy, right? But you can also have another type of pressure that is going to become very important when we study the stages of star formation. So here it is, that's the typical molecular cloud. And as I said, you can have a few hundred solar masses, and that will be kind of enough for gravity to start overcoming pressure. All right. The emission line of molecules like the carbon monoxide, right? They prevent this from happening, right? The pressure from building up. And then they can convert thermal energy into infrared and radio photons, which is why we can actually see them in those wavelengths. Okay. So that's important. The mass, and remember I told you that they are very vast in terms of parsecs. All right. So that's stage one, by the way. We are still on stage one. We are in the molecular cloud section. Another resistance for gravity can be other forces acting on the cloud, because you have thermal radiation and you have random motion of atoms. We know from physics 1 or physics 2 that there can be magnetic fields being produced, right? These magnetic fields allow charges to move along the blue lines, like in a spiral move, right? Because there's also an electric force in there. Now, there can be friction between those particles and the neutral particles, and then they can both oppose the force of gravity, all right? The magnetic force and the friction force between particles, okay? So as it says here, the magnetic fields and the turbulent gas inside the cloud, they increase resistance to gravity. They form an opposition to gravity. All right. So it's important to know this, to know the emission lines pressure, right? Or the emission lines preventing the pressure building up inside the cloud, and the properties of a cloud. All right. So now that we know that, are there any questions? This is just stage one, okay? Stage one will be the molecular or interstellar cloud. How big it is, how massive it is, and what forces are acting. And the battle between gravity and pressure that is about to happen. Okay? So let's suppose, not only suppose, now let's go into the second part, the second stage. When a cloud starts to collapse. When a cloud starts to collapse, then you have the process of fragmentation. And this process can produce either a few dozen stars, some may be larger than the sun, or a whole cluster of hundreds of stars. It depends on the size of the fragment. And it also depends on how these are originated. All right. What we think about the sun, and I mentioned this on chapter 14, what we think is that the sun was formed as part of a group of stars, but because of gravity, it was probably ejected from a larger system. Lucky for us, right? Because if the sun was part of a system, life on Earth would be much different, if there will be any life, right? So in the process of fragmentation, gravity within the contracting fragment or gas will start becoming stronger. And then the gas becomes denser, more massive. Because you have to think that a fragment will be a very tiny part of the whole volume of the cloud. So you have a large amount of mass of the gas in a very small volume. Density is mass over volume, so you have a more dense region. So then gravity can start overcoming the pressure. And then this can start breaking the cloud in more smaller pieces. Then you have more fragments. So a turbulent cloud can contain approximately 50 solar masses of gas. All right. That's for a cloud that is already unstable. There you are, a more realistic picture of that. The reason why it looks like that is because of what's happening when in the process of fragmentation, right? In the process of fragmentation, normally what you have is a trigger, right? It can be a shock wave or a supernova, as I mentioned, and that will create random motions of particles inside the cloud. You also have to remember that as the cloud starts to contract and as the pressure starts to build due to gravity, then you have higher temperatures. I mean, let's write this equation. Let's see if you remember. PV equals to nRT. So if you increment the pressure in some of these regions, and you assume the volume to be, the change on volume to be negligible, the temperature has to go up. And if the temperature goes up, these guys becomes more and more larger, right? The random motions. In gases, we call it the root mean square speed of particles in a gas. That is proportional to the temperature of the gas. All right, the kinetic energy of particles. Okay. So a fragment to form a star like the sun must contain 1 to 2 solar masses. And the size should be 100 times the size of a solar system. So in between, I want to show you what happens with larger stars. But just to give you a perspective, right? For a star like the sun, you need to have a very big fragment, right? Because you have to think about all the material that is going to be ejected towards the end. All right. So it says that each fragment of the cloud where gravity is overcoming pressure, so that is what we call gravitational contraction, then it can start becoming a star. All right. A larger cloud will normally create a cluster of stars. So it all depends on the process of fragmentation and how big the fragments are. All right. So now there is no more cloud, but there is a whole bunch of fragments. Now, the process of between the process of fragmentation and when it stops, you can have several tens of thousands of years. Okay. So it takes a long time from the point it begins contracting to the point where the fragmentation seems to stop. All right. So now let's talk about the different type of star formations that can happen. You can have a small fragment that will give you a single star, like that. Or you can have a larger fragment, right? Where you can have a cluster of stars. What do you think will be the answer for this? What will happen to a contracting cloud if we're not able to radiate away its thermal energy?
Let's see.
Yeah,
it's gotta be something in terms of like increasing.
Yeah, you cannot have decreasing temperature, or temperature cannot remain constant. The mass cannot increase because you are talking about contracting, so it has to be the pressure has to increase. Okay, that's because the energy is being contained. So if the energy is being contained, then by pressure, okay, I know this is the ideal gas equation, and it's not really the equation that we will use for this type of gases. There is a real gas equation, but it's similar to this anyway. But Boyle's law still holds, all right? Or this will be Charles' law. If the pressure builds up, then that means that the temperature is increasing. So, yeah, all right? So that's, see? Okay, let's make a parenthesis now. What about the first stars? When after the Big Bang happened, after the dark eras or the dark ages, and after the recombination period, right? When you start having helium, hydrogen being formed, elements like carbon and oxygen had not been made because we know they are made in the core of stars. So how did these stars were formed? What we know is that there were not enough CO molecules to provide the cooling, right? That's the idea, that's the main reason why we care about CO molecules, is because of the cooling, right? So most of these clouds had to be formed or most of the stars had to be larger and warmer. And the molecular clouds had to be warmer as well. All right? And for gravity to overcome pressure, they had to be more massive. So a star like the sun will not have been able to be produced or born yet. Right? We're talking about the first stars that were produced or were born in the universe. All right? So what are the characteristics of the cloud that produced or that where the stars were actually born, right? These first stars. So by doing simulations, instead of having carbon and oxygen, we just replace them with hydrogen molecules. And what we know is that for a molecular cloud to have enough mass and to be able to contract and start igniting a star, you need to have 100 to 300 kelvins of temperatures. So if you go to 300 kelvins, you're talking about 1 degree Celsius. 1 point something degrees Celsius. So way higher than the normal molecular cloud we've been talking about. And there has to be at least 200 times the mass of the sun of gas to be able to start overcoming the pressure and be able to contract and shrink. All right. So, well, 100 to 200 times the mass of the sun. All right. So that is the characteristic of a very old star-forming cloud, and what we should take into account when we realize that there was no carbon monoxide, right? Because they were produced before the first stars were born. So what was the aim of this part of the lesson? Was first to know where stars are formed in molecular clouds, the composition of these, and how we study them, hydrogen there, H2, and carbon monoxide. We studied the emissions of carbon monoxide, and we know they stay cool by the cooling law of carbon monoxide, by the way. There's a whole equation for that. And the temperatures for these clouds, between 10 and 30 kelvins. They can be found also up to almost 100 kelvins, but that's not very common. 10 to 30 kelvin seems to be the range, unless you're talking about the first stars, where, as I just showed you, they had to be warmer for the mass to be actually able to overcome gravity and then able to produce stars, right? Why do they form? Because these clouds are triggered they become unstable and they can start to fragment. Once they start to fragment, you have different lumps of this cloud, and each of those lumps can start to contract and shrink, and enough pressure can be built to start igniting enough heat to have a star being formed. But there's a whole process happening in there though, right? I mean, it's not just a fragment contracting though. It takes a long time, in some cases millions of years, for a fragment to become a star, like for example, a star like the sun. So those were stage 1 and 2, right? The molecular cloud and the fragmentation process. Now we're gonna go to the stages of starbirth. Now we're gonna be analyzing the slow contraction of a star forming cloud, because there's a point where the cloud starts slowing down as it contracts. And then we're gonna see how important is rotation for the birth of a star, and how does nuclear fusion begin. Okay, so remember that besides gravity, thermal radiation, and pressure, we also care about density, specifically the density of the inner region of the fragment, right? Which has to be very high, hence should be heating up very quickly, right? In the outer parts of the fragment, right, the temperature is still sort of low, and the density keeps increasing as it goes towards the center. So that makes sense when you remember the structure of a star, right? The core of a star is the densest part of the star. And then as you go to the outer envelopes, the density starts to decrease. We saw that with the sun, right? What causes the contraction to slow? Random motions in the cloud. All right. When gravity starts overcoming pressure, right, you start having more dense matter inside. And if you have more dense matter, you have more temperature, right? More radiation, right? And this will increase the random motions between particles. So then you have more collisions, more friction, right? And then you have that the infrared and radio photons, they cannot really escape, right? So then you have thermal energy building inside. That will start slowing down the contraction. All right, let's go back to this. The fragment cannot contract eternally, right? There is a threshold point where the energy trapped inside by the pressure and the temperature, right, is the photons are trapped by that. And then they have enough energy to produce pressure or a force to stop down the contraction. It's similar to hydrostatic equilibrium, but it's not hydrostatic equilibrium, because hydrostatic equilibrium, guys, is when a star is in the main sequence. But this is not a star yet. We're getting to that point in a few 100,000 years. But right now, there is a battle between the contraction due to gravity and the pressure building inside. That's what we call this stage, the gravitational contraction era. All right. Right now, the energy building inside a star is due to gravitational contraction. And if you remember, when we study the sun, and when we want to analyze the life of a star like the sun, one of the ways we were trying to analyze it was by gravitational contraction. And we realized that that wasn't enough. If a star like the sun was in equilibrium due to gravitational contraction, that will give you only a few 100,000 years. But we know the sun has been up there for 4.5, almost 5 billion years. And it's going to be there for at least 5 billion years more until it collapses into a red giant. So then we know that there has to be something else, which is nuclear fusion. So before we get to that point, the pressure inside and the gravity are sort of oscillating in a sort of stabilized, how do you call this? Period of time. Okay. This has a name. We are in the protostar period. The protostar period resembles a star. In the center, you have the protostar, which is surrounded normally by a large disk of gas and dust and high energy particles. Look, don't get confused by a black hole when I mention a creation disk. But yes, there is a point where a protostar will have in the edge of a protostar, you can have an accretion disk. In fact, let's see what we have here. All right. Let me give you a description of a protostar. As a protostar evolves, right, it shrinks, right, because of the contraction. That proves that there is no equilibrium as of yet. As it shrinks, the density grows, more mass in a smaller volume, and makes sense, right? The temperature will start to rise. This normally happens 100,000 years after the fragment was formed, right? And the temperature of the protostar, of the inside region, of the inner region of a protostar, is of approximately 1 million kelvins. Awesome. So we're already in the million kelvins. But if you remember, the temperature to fuse hydrogen to helium is 10 to 15 million kelvins. So we're still a long way to go. This protostar is normally very, very much larger than the sun. In terms of size, think it as the size of the orbit of Mercury. So imagine the sun was as big as the size of the orbit of Mercury. All right, but that's not it. The protostar is surrounded by a protostellar disk, which can be approximately 100 AU. 1 AU is the distance from the Earth to the sun, so 100 times that. This will take you to, or this is basically the general picture of a protostar. All right. There you are. So yes, this may look similar to pictures that you have seen of a black hole, but they are not. What you see there right now is what we call in astronomy, and I don't think it's in the book, a T Tauri star. I'm gonna write it here. If you remember the video of dead stars that we watched at the beginning of the semester, they talk about dead stars, but there is a point where they talk about jets. Jets are not just produced by stars dying, like gamma ray jets, or gamma ray particles, or gamma ray bursts, right? You can also have jets due to T Tauri stars. This happens due to the rotation in starbirth. As the protostellar disk, or as the protostar is shrinking, right? Remember that we are in a 3D space. So you have to imagine a cloud in the 3D space, right? But as it shrinks, the disk starts to flatten. And as it shrinks and flattens, the disk starts rotating much more rapidly. Imagine, okay. This is because of the conservation of angular momentum. And we did that in chapter 4, right? When a ballerina is dancing and bringing her arms towards her body, she will start spinning more rapidly, right? That's exactly what's happening in here. As the disk shrinks and flattens, the disk will start rotating more rapidly. And that could potentially ignite these jets of high energy particles, which are good because this allows the envelope of gas to be ejected away. And then it will start taking you to the last part of a star birth, which will take you to the formation of a star, like the sun. And then you have material surrounding it. All right. That material can be used for what? For planetary formation. So the role for rotation is for this to happen and also for planets to be formed. Planets are not formed out of nowhere. Planets are formed from the stellar disk that was surrounded, the protostar, and that was ejected away in the last stages. This is actually called a solar nebula as well. And we call it a solar nebula because we know this is true because we have been able to extrapolate how the sun was formed. And we know that was how the sun was formed. All right. In the first part of this course, we teach about the formation of the solar system. And this stellar or protostellar disk is where planetesimals were formed. It's right now very hot, especially as you go closer to the protostar. But as it goes and is ejected away, it starts cooling down, and that forms planetesimals. As the planetesimals join together due to gravity, they start forming planets. Let me ask you a question. Based on what I told you, which planet do you think was formed first in our solar system?
I want to say it's one of the gas giants, considering I remember somewhere that Jupiter was like steps away from becoming like a second sun, but kind of like pooped out at the last minute for reasons I can't remember.
Yeah, so Jupiter was actually the first planet to be formed. Yeah, that's good. Because the gas giants are mostly made of the remnants of that proto disk that was ejected away when the sun was formed. Look at this. You have the cloud. The contraction produces a fragment. This fragment starts to shrink, right, and contract. So when you have that flattening and contraction, you start having this protostellar disk and the protostar there. The conservation of angular momentum will ensure that the rotation speeds up as the cloud shrinks. And then you have these jets being formed, right? And as I said, we know that's right because that's basically the foundation for the theory of the solar system formation, right? The gas giants and meteorites give us a lot of history of the formation of the solar system, by the way. So we know the abundance of elements 4.5 billion years ago. Jupiter and Saturn, also Neptune and Uranus, but Jupiter and Saturn in particular have a very small density, and they are mostly made of hydrogen and helium. That hydrogen and helium didn't come out of nowhere. They came from this disk. Now, what's happening with Mercury, Venus, the Earth, and Mars? Why are they solid rock? Because once the envelope of gas was ejected, nearby the star, like the sun, or nearby the sun, there were fragments that started to cool. As they started to cool, what do you think happened? There was some sort of solidification. So they start having a different composition and they became more solid, aka planetesimals. And they started to form planets, the terrestrial planets. But that's a different type of, well, that's related to this anyway. Okay, so the rotation speed of the cloud increases as the cloud contracts and flattens. Very important that, all right? And then you have, so let's see. So even though the temperature is high, to counteract the gravitational pull, again, at this stage, balance is not perfect yet, guys. The contraction is slowing down, but it's not stopping completely. Okay? So at the end of this stage, right, there is a strong protostellar wind, right? This wind can be ejected by these jets that you see in the picture. That is the T Tauri phase that I was talking to you guys about. All right. Now, the protostar starts approaching the main sequence. It has shrunk about 10 times the size of the sun. And the temperature of the surface of the protostar is now about 4,000 kelvins. But this is when the evolution starts slowing down. And the reason is because of heat. Contraction is normally going by a large rate, right, of the energy radiated to space. All right. And what happens is that there is, again, a problem with the pressure that we're going to be discussing in a second. All right. So remember, right now we are almost getting to the point where the protostar is about to eject all those outer envelopes and is going to get hot enough inside, right? Inside to be able to start producing nuclear fusion. Okay, so the idea with flattening is due to the collisions between particles. All right, this collision plus gravity will help the cloud to start flattening into this stellar disk. All right. Now, obviously, if you have collisions, the velocity or random motion of particles starts slowing down. All right. So then as the spinning cloud flattens, it also shrinks. All right. This is very important, all right, because now we're getting into the phase between a protostar and a main sequence star. From the process of fragmentation to the stellar disk, right? Shrinking and contracting, speeding up, becoming a T Tauri star, and then flattening due to collision of particles. All right. Any questions about this? So obviously these jets, they have to do with the particles that are being, so here's what I'm going to mention. I'm going to mention the accretion disk. So similarly to a black hole, it's not the same, but there is a disk of high energy particles that are being produced nearby the protostar. That's because as the cloud shrinks and contracts, it's speeding up. So that gives energy to the particles. And we also know that there are magnetic fields inside that region, right? The sun has strong magnetic fields. So the protostar is also expected to have magnetic fields. So at some point, right, this rotation will produce those jets, right, coming from the protostar, which are characterized by these T Tauri stars. All right. So this is an example of a jet. And just to give you a scale, that size of the picture is 1,000 EUs. Right? We're talking about distances that go beyond, way larger than the size of the solar system. All right. But once that happens, So here's another, this will be more like a radio image of it. All right, so that's your protostar there, and that's your flow of jets. Normally, this indicates almost the end game for the protostar. That's when you start going into the star being born inside and start having nuclear reactions happening in the core. Okay, one question. What will happen to a protostar that doesn't rotate? Because that could happen. They are not very common to be observed, though. So what will happen if you have if a protostar is formed but doesn't rotate? Jets won't be produced. It needs to have rotation, so A is one. Why is rotation important? Because you have the disk forming. And what comes from the disk?
It should be, if what you're suggesting is true, then it should be it'd be very bright and infrared light C.
It doesn't matter if it's rotating or not. It will always be bright in infrared. So that's not a condition.
Okay.
So would it be?
Is it B?
Yeah, it will be B.
Yeah, process of elimination. Yeah, it wouldn't be round. That's kind of like out there. All planets are round. That's just how gravity works.
Yeah, I mean, it will not form planets, or it will not easily form planets, because without the stellar disk or the protostellar disk, there is no gas or material being able to be ejected to get planets to be formed. So that will be B. All right. All right. So, by the way, just to give you guys extra information, everything that we have been describing fits very well for a star approximately the size of the sun. It can be slightly bigger as well. Temperature, density, and pressure for stellar objects of other masses, they exhibit similar trends. The difference, though, is the size of the protostar. What do I mean by that? Remember that the core of a star formation is the fragment of the molecular cloud. Granted, you can have a very big fragment and you can have a star cluster, but you can also have a fragment big enough to produce a couple of very massive stars, like O or B stars. So a more massive fragment will produce a more massive protostar, hence a more massive main sequence star. All right. So once the protostar blows the gas away, right? Most of the energy is coming still from gravitational contraction. But contraction will continue until you reach temperatures of 10 to 15 million kelvins. That's when contraction stops. That's when it fully stops. Because that's when you have the hydrogen that is mostly abundant in the protostar burning into helium. That's when you have the star being born into a main sequence star. So remember, everything we have discussed up until this point was governed by pressure fighting with gravity in what we call the gravitational contraction. You have shrinking, fragmentation, shrinking, flattening, speeding up the production of a T Tauri star, protostellar disk, protostar, ejection of the disk, the jets of gas and particles being, shoot away, and then you have contraction up until the point where you have fusion in the core, which allows for this to happen. The PP chain reaction, right? Proton-proton chain reaction, right? So and that happens with every star. Every star in the universe is born by fusing hydrogen into helium, right? Remember that more than 80% of the stars that we can observe are in the main sequence line or queue. Okay. So look, I know I said, and I'm going to talk about brown dwarfs as well in, yeah, we probably have time to do that. I know I said that H&R diagrams are used to locate stars, but they can be helpful to understand everything we have been discussing. Because once you start talking about a protostar, at the moment you start talking about a protostar, that's when you start having luminosity and temperature. And if you have luminosity and temperature, what do you have? You have, you can start locating them in the H&R diagram. And here it is. So in the H&R diagram, we had that the lowest temperature was 3000. But remember that there is a stage for the protostar where it was large enough and hot enough, around 4000 kelvins, to be placed in the H&R diagram. Now, as the protostars is being born and assembling, you are in stage 1. So from the cloud, fragmentation, shrinking, contraction, flattening, all that is happening here, right? Until you have the protostar. Look how I only have the arrows like that. Why don't I have arrows coming out? Why I only have these green arrows here?
Yeah, they're all yeah, so it should be like gravity or something.
Yeah, that's gravitational contraction. Remember, for the protostar, the only force acting is the gravity, is gravitational contraction. The reason why it seems to be stable, even though it's not really, is because the pressure in the center is slowing the contraction. It hasn't stopped it yet. Okay. So in stage 2 and 3, that's when the luminosity and temperature are high enough to be placed around the giant region, right? If you remember, this is the main sequence region. This is the giant region. In fact, this is the supergiant region here. So a protostar can easily fit in here. The difference is that it's unstable. So it will very quickly go into stage 2, 3, and then until it reaches stage 4. In stage 4, or as we call it in astronomy, protostar stage 4, that is when fusion rate starts to begin. Oh, sorry. That's when fusion rate starts. And then that's when you have a balance between fusion reactions and gravity. All right. So that's for a star like the sun. What about a star like Deneb or Rigel? This process will be the same. It just will reach equilibrium around here, like that. In fact, let me show you that. So this is the assembly of a protostar, all right? This is the contraction here. 3000 kelvins around here. And then 4000 kelvins will be around here, right? Yes, sir. But let me show you this slide. There you are, that's the one. So this slide is very important because it shows you the track for stars of different masses. So when you model this, we get that, as you expect, high massive stars like giant or supergiant stars, or sorry, blue giant stars, they reach from protostar contraction and shrinking to main sequence in approximately 60,000 years. However, a star like the sun requires 30 million years to go from protostar to main sequence. That's a long time. And that's without taking into consideration all the time it takes from the fragmentation to become a protostellar disk and then a protostar. Right? So it's a long time. In fact, you could easily say that a star like the sun, from the process of fragmentation until it became like the sun that we see now, it could easily go beyond the billions of years. Right? But that's okay because they do live for a long time, right? So that's why we can see them a lot in the universe. However, the very short amount of time it takes for a giant star to become a main sequence and then to die indicates that they have a very short lifespan, which is why we don't see many of them in the universe. We see them, but not at the same rate as the main sequence, as a low mass star. Okay. Remember that to locate stars in the H&R diagram, you need to know the luminosity and the surface temperature. Right? Now, we can use the H&R diagram to look at the process a star follows to become a main sequence. But we know we cannot use the H&R diagram to locate protostars because they are not stable enough. Even though for the sun it takes 30 million years, right? But if you compare that to the age of the sun, that's nothing. The age of the sun is 10 billion years. So. All right. So that was the main idea of this section here. What slows the construction? What's the role of rotation? The conservation of angular momentum. All right. Remember, to slow the contraction, you need to have pressure building up. So you need to have trapped energy, trapped infrared or radio photons inside. So they cannot escape. So they can actually slow the contraction. They don't stop it, but they can slow it to eventually make it go into a main sequence star. Okay, so this is also very simple. All right. Here it is. Let's talk about failed stars, which is related to this. This, for example. Okay. So, as you expect, not all the fragments will produce stars. Some fragments are too small to ever become stars. Let's talk about Jupiter. Jupiter is a good example, but Jupiter is not a brown dwarf. So Jupiter is not really a failed star. Let's explain why. Jupiter was formed as the first planet of the solar system, and it was formed in the sun's protostellar disk. All right, in the nebula when the sun ejected it. And we can still detect part of this heat, by the way, when we analyze the emission lines from Jupiter. But the planet didn't have enough mass for gravity to crush matter and to produce nuclear reactions. Instead, Jupiter became stabilized by heat and rotation. So, you know how I was talking to you guys about how you can slow contraction by building pressure? That's sort of what happened with Jupiter. It was able to become stable just by heat and rotation before the central temperature became hot enough to produce nuclear reactions. Low mass fragments, like for example in that case, they just don't have enough mass to initiate nuclear burning, right? So what's the model that we have for these failed stars? or what's the model that we have for a star to be considered a brown dwarf, which is actually a failed star. Jupiter is not a brown dwarf, but Jupiter is a good example of a planet that was close, not very close, but close to become a failed star. The minimum mass for the gas to generate enough temperature for nuclear fusion is 0.08 times the mass of the sun. 8%. In terms of the mass of Jupiter, that's 80 times the mass of Jupiter. So Jupiter was very, so Jupiter didn't have enough mass for that to happen. All right. In astronomy, right, we have the term brown dwarf to a low mass fragment of about 12 times the mass of Jupiter. Okay, let's repeat that because there's a lot of numbers there, right? So for a fragment, the minimum mass, the smallest mass, I think it's here actually. No, it's not here, right? Yeah, no. The smallest mass for a fragment to start burning, to eventually start burning hydrogen is 0.08 the mass of the sun, which is approximately 80 times the mass of Jupiter. A failed star, which we call brown dwarfs, are normally, let's put this is a brown dwarf, kind of greater than or equal to 12 times the mass of Jupiter. So between, right, that value, you should actually have a brown dwarf, which was very close. I mean, there's a point where fusion was about to happen, but it wasn't stable enough to continue, so that's why. Okay. Any questions about that? No?
I think we're fine.
Remember that fusion will not begin in a contracting cloud unless you have above 10 million kelvins. All right. Thermal pressure cannot stop contraction because the star is constant. Okay. So yes, thermal pressure is not enough to stop contraction, guys, because it's always losing energy. If you lose energy, this will decrease. So it won't be stable. All right. So is there another form of, okay. Yes. So thermal pressure is not enough. So how come you can actually slow contraction enough to get to this point? Okay. This is what happens in white dwarfs, and we are gonna go back to this eventually. All right. In chemistry, there is something called the Pauli principle. When you guys did, well, if you haven't done it, let's just go very quickly. You have the quantum numbers, quantum stages, right? And electrons can be modeled in using the quantum numbers, right? There's the primary, the angular, the magnetic, and the spin. And what we know is that in an atom, two electrons cannot share the same quantum state. And they use this nice analogy. They use people and chairs. Each person can only sit in one chair. You cannot have two people sitting in one chair. What happens is that there is a point when pressure has shrunk the core so much that the number of electrons is approaching the same number of available quantum states. So finding this available state requires electrons to move faster. This creates degeneracy pressure. So this is when you have electrons not being able to occupy the same state in the same place. That's when these electrons are moving faster, that will produce higher temperatures, that will produce higher pressure. That, in combination with thermal pressure, can start helping you slow the contraction of a cloud. All right, so that's another important aspect there for star formation. And yes, we will talk about this when we talk about white dwarfs, because what happens in a white dwarf is that, again, in a white dwarf, there is a contraction because there is no more heat being produced in the core, right? There is a collapse. And then again, you will get to this point. And that's why white dwarfs are made of electron degenerated matter. All right, there is a huge amount of degeneracy happening in there. So again, there are two types of pressure: thermal pressure that depends on heat, degeneracy pressure, the degeneracy pressure that depends on particles and the Pauli principle. All right, quantum states. And well, oh, here was a number. So there is the there is the threshold limit, right? For masses that go less than 0.08 the mass of the sun, that's when the core can become hot enough for fusion, right? For masses that are below that and above the 12 times the mass of Jupiter, you have brown dwarfs. All right, and it's not something that we invented, by the way. We have found brown dwarfs in the universe. In Orion, for example, all right, we have found some of those. And in other interstellar clouds that we have observed star formation. All right, so let's leave it like that. The last thing we have to do is clusters, okay? We will do that on Wednesday. Are there any questions about this? So
No, Professor.
it's not that bad, right? I mean, we will go back, I will try to go back and do a summary of all these processes, but there are some key words that we have to focus, like fragmentation, shrinking, pressure and heat, gravity, and the whole concept of protostar or protosun.